So, good evening, everyone.
Good evening,
Today,
sir.
today we are going to have a recapitulation of the concepts that we have learned in week two. So, let me first introduce myself. My name is Shubham Rai, and I'm a PhD research scholar in Department of Applied Mechanics, IIT Delhi. So, let's start. So, in week two, you would have studied about lecture four. Lecture four was based on transformation of stress vector. Lecture five was based on stress equilibrium equations. And you obtain stress equilibrium equations by using the balance of linear momentum, right? So firstly, you would have learned about transformation of stress matrix. Actually, it's not a vector, so it's a tensor. So stress matrix, it's a second order tensor which is represented by matrix. So you would have learned about transformation of stress matrix. Like suppose you have one coordinate system and you have rotated that coordinate system to arrive at some another coordinate system. So how will you represent stresses in the new coordinate system that you would have learned? In lecture 5, Sir had derived balance of linear momentum, and from that he obtained stress equilibrium equations. Now, lecture 6 was based on balance of angular momentum. You would have studied all these fundamental laws in class 11th and 12th as well. But here we are going to apply these laws to the field of solid mechanics, right? So, although these are valid for fluid mechanics also, but here, since the course is concerned with solid mechanics, so we'll apply them for solid mechanics. So firstly, I'll try to give a brief overview of lecture 4, 5, and 6. Then we'll start with some practice questions. So let me just start with brief overview of lecture 4. So let me start with lecture 4. So lecture 4 was based on transformation of stress matrix. So let's say you have, so transformation of stress matrix. So let's say you have sigma as a stress tensor, and you have that in coordinate system E1, E2, E3. So that can be represented by, let's say you have three traction vectors also on the plane normals having, on the planes having their plane normal as E1, E2, E3. So the stress will be represented by first column of the stress tensor will be this traction vector on a plane having plane normal 1, and then second column will be traction vector on a plane with plane normal E2, and third will be traction vector on traction vector with on a plane with plane normal E3. So this will be your stress tensor in the coordinate system E1, E2, E3. Now let's say, so you also can write it in terms of initial notations. So you can also write it like sigma ij, that will be equal to jth traction vector and dotted with ith basis vector, right? So you can write also like this. So it's the same thing actually. So as I told you that this j here represents the plane normal, and I here represents the direction in which we are taking the traction. So it means, let's say we write sigma 1, 2. So that will be T vector and it will be 2 dot E1, right? So what that will be? So it will be T12. T12 because we are dotting with, so we are taking traction vector on a plane with plane normal E2. And then we are finding the component of that traction vector in E1 direction. Okay, so that will give you the first component of traction vector. I mean, first component that will be first component of any traction vector in E1, E2, E3 coordinate system will be in traction E1. So that will give you first component of the traction vector on a plane with plane normal to E2. Okay, so this is another notation. This you would have studied in week 1 classes. Now, let's say we want to rotate this stress tensor. So how we will do that? So let's say in new coordinate system, sigma is denoted by sigma ij hat. Okay, so sigma ij hat will be written as sigma ij hat. So that will be written as traction vector. Now this traction vector will also have to take in the coordinate system E1 hat, E2 hat, E3 hat. So traction vector with plane normal ej hat, traction vector on a plane with plane normal ej hat dotted with ei hat, right? So that will give you ith component, I mean sigma ij hat. So, and that is not, I mean, this representation is not equal to this representation, Tj normal T, I mean, Tj dot ei. They are not equal because representation is different. Obviously, stress tensor is same, but its representation is changing from one coordinate system to another coordinate system, right? So, and I'm just going to write the relationship between sigma ij hat and sigma ij. So that will be, so let me write. These things you would have studied in the class, but I'm just recapitulating them. Relationship between sigma ij and sigma ij hat. That will be, so sigma ij hat, that will be equal to sigma k to sigma m, sigma mk rmi rkg. So if I just write in terms of initial notations, I can drop this sigma, I mean capital sigma terms, because summation terms, because if indices is repeating, it means we are going to sum it up. So here k is getting repeated 2 times. So it means there will be summation over k, and m is also getting repeated 2 times. So there will be summation over m. So even if I do not write these summation signs, it is obvious that there's going to be summation over k and m. So what I'm going to do is, this will be rmi sigma mk times rkj. So if you see here, so the so firstly these two matrices are getting multiplied. So rmk times rkj will give you some matrix. Let's say amj, right? So what I'm saying is, let's say multiplication of these two will give you amj. Now here, because these two indices, I mean column of first matrix and row of second matrix should be same. So that only then matrix multiplication is possible. That's why k here, k should be same here for both of these. Now, but if you see here, so this is RMI and AMJ. In ideal situation, it would have been RIM AMJ, but it is RMI, means we are taking transpose of R here. Actually. So what we will do is we will write it like this: RIM transpose sigma MK and RKJ So that will imply sigma I hat. You can stop me if you have any questions. So if I write it in terms of matrix notation, so sorry. If I write in terms of matrix notation, so that will be sigma. That will be R transpose. So R is rotation matrix or rotation tensor. So R transpose sigma R, right? And these three are in E1, E2, E3 coordinate system. Because sigma, this sigma is E1, E2, E3, this R will also be in E1, E2, E3 coordinate system, and this kept, I mean, and the new sigma hat that you obtain, so that is in E1 hat, E2 hat, E3 hat coordinate system. Okay. So this is the formula. Now, let's say you want to transform a vector. So transformation of vector will be, so what was the formula for transformation of vector? You remember from the class? So let me just write it. Vector component. Transformation of vector component will be, let's say you have v vector here, v hat vector, and that was expressed in E1 hat, E2 hat, and E3 hat coordinate system. So that will be nothing but simply R transpose, rotation matrix transpose times the v vector in E1, E2, E3 coordinate system. Okay, so that will be it. So let me just write. This was the overview of lecture 4. And let me give you an overview of lecture 5. In lecture 4, we learned about transformation of stresses from one coordinate system to other coordinate system and transformation of vectors from one coordinate to another coordinate system. So now let's go to lecture 5. So in lecture 5, we learned about stress equilibrium equations. I'm just going to write them. Here we have stress equilibrium equations. So you know that using Newton's second law of motion, so external force applied on a body is equal to rate of change of linear momentum. That is uh, Newton's second law of motion. So let's just write it. So all the summation of all the external forces that are acting on the body. So that should be equal to the rate of change of linear momentum. And rate of change of linear momentum can be written as let's say a mass of the body, total mass of the body times acceleration of center of mass of the body. Right? So this external force had two components. So external force can be due to traction applied on the body, or there may be some body force. So traction is like, let's say with a rope, you are pulling a body at a point. So that will be a point load. And traction will be some distributed load that you are applying on the surface of the body. And body force will be like that will act upon volume of the body, like gravity. Okay, so external force can have contribution from traction as well as body forces. So traction component of external force was, I'm just writing as F track. So that was equal to You can see the detailed derivation in the lectures. But the final expression was sigma is equal to 1, 2, 3 del sigma by del xi times, I mean, sigma will be obviously tensor times ei and times delta v. And this will be a vector because this is tensor and you are differentiating it with a scalar, so that will remain second order tensor only, and you are multiplying it with the vector. So second order tensor multiplied with a vector will be vector. Okay, so that is equal to external. That will be equal to traction component of the external force. So this delta V is the small volume of the keyword that was considered in the class. So second, we have body force component. So that was simply final expression was the body force multiplied with delta V. Right. So if you apply linear momentum balance, so if you put these two expressions on the left hand side, I mean F external will be F track plus FB, and you equate it to right hand side, and you bring this mass of the body to the left hand side. So finally, what will you get? So I mean, let me just write. So you will get sigma is equal to 1 to 3 del sigma by del xi times ei delta v plus v delta v minus MACM, right? And A is also obviously a vector. So that should be equal to 0 vector. So null vector. So now if you divide the whole equation with delta V, so you'll get M over delta V, that will be the density of the body. So finally you will get del sigma over del xi times EI, and I is equal to 1, 2, 3 delta V plus, well, so delta V will not be there because we have already divided the whole equation by delta V minus rho, that will be density, and is. So this was linear momentum balance equation. So if you try to write this equation in terms of coordinate, in terms of differentials, so what will you get? So let's write this equation down. So let's write this equation for I is equal to 1 first. So when I will be equal to 1, so this will be del sigma by del x1. Sigma is nothing but sigma 1 1. So let me write this equation. So del sigma by del xi. So del x1. So that will be nothing but del sigma 1 1 over del x1, del sigma 1 2 over del x1, del sigma 1 3 over del x1, and del sigma 2 1 over del x1, del sigma 2 2 over del x1, del sigma 2 3 over del x1, right? And here you have del sigma 3 1 over del x1, del sigma 3 2 over del x1, and del sigma 3 3 over del x1. And this is what you have del sigma by del x1. And if you multiply this with by E1, because first term will be del sigma by del x1 times E1. So if you multiply this with E1, so let's write it here. This will be a matrix times a vector, which is E1. E1 will be represented by 1 0 0, right? Because that is in the direction 1. So now if you multiply, so you will get first column of this matrix. Okay. Similarly, if you try to find out del sigma by del x2, so you will get second, and you multiply with E2, you will get second column of that matrix. And similarly, if you find del sigma by del x3 and multiply with E3, you will get third column of that matrix. So finally, with this expression, what you're going to get is, let me just write it down. So you're going to get, so if you put I equal 1, you're going to get del sigma 1 1 by del x1, del sigma 2 1 by del x1, del sigma 3 1 by del x1. So this is corresponding to I is equal to 1, and then you have I is equal to 2. So del sigma 1 2 by del x2, del sigma 2 2 by del x2, and del sigma 3 2 by del x2. Right. As third I is equal to 3, you will get del sigma 1 3 by del x3, del sigma 2 3 by del x3, and del sigma 3 3 by del x. Plus you have this b, so b also will have three components, b1 b2 b3. So it's, and I'm just writing equal to, I'll take this term go into ACM to the right hand side, so that will be, I'm just denoting ACM acceleration of center of mass of the body. So in lectures you would have seen that we had taken firstly cuboid and then we shrink that cuboid to the small volumes, so that will become a point. So the center of mass will essentially become a point. So I'm, instead of writing ACM, I'm just writing A. So that will be a acceleration of a point in the body. So that will be rho times rho A1, rho A2, rho A3. So if you're able to see, these are three equations. First is this equation, second is this equation, and third is this equation. So try to write it down in terms of in E1, E2, E3 coordinate system. So I can just write LMB in E1, E2, E3 coordinate system. And then that will be del sigma 1 by del x1 plus. Just wait a minute, I'm getting a important call. Okay, sorry for the interruption. So first equation will be del sigma 1 2 over del x2. I'm just writing the first row of this whole equation. Row A1, right? And similarly, you can write second and third row. So instead of writing sigma 21, I'm writing tau 21 because we represent shear stress with tau. So sig tau 21 over del x1. I mean, here also I'll have to replace. Let's keep it sigma 21 only. Right, so I'm just writing del sigma 31 over del x3, del x1, del sigma 32 over del x2, del sigma 33 over del x3 plus b3 is equal to rho 8, right? So this is the final equation that you have. You have three differential equations, first, second, and third. So essentially, first equation in the lectures you would also seen, you would also learn that the first equation represents the equilibrium in direction 1. Second equation represents equilibrium in direction 2. Third equation represents equilibrium in direction E3. I mean E1, E2, E3. So you also can, so instead of writing this whole set of equation, you can write this equation in initial notation. So that can be written as sigma ij comma j plus bi is equal to rho ai. That is the final equation. See, initial notation has a lot of advantage that you can write this much linear equation in just one line, 3 words. Okay, so here comma represents the differentiation. So let me just derive it for the first row. So if let's say I is equal to 1, so I is not repeating indices. So in a particular expression, in a particular expression, it is not repeating. So I here is not repeating, but j is repeating. So there will be summation over j. Let's say I is equal to 1. So it will be sigma 1 1 comma 1 plus sigma 1 2 comma 2 plus sigma 1 3 comma 3. 1 1 comma 1 means sigma 1 1 will be differentiated with respect to x1. So first term will be del sigma 1 1 over del x1, and then sigma 1 2 comma 2 will be del sigma 1 2 over del x2, and sigma 1 3 comma 3 will be del sigma 1 3 over del x3 plus b1 is equal to rho a1. So you get the first equation. Similarly, you can get other two also. Okay, let me move to the lecture 6. So this was all about lecture 5, where you will have learned about derivation of linear momentum balance equations. So that gives you equilibrium equations, stress equilibrium equations. Now going on to, so you can remember just this equation finally. Sigma ij comma j plus bi is equal to rho ai. So finally, in lecture 6, you would have learned about angular momentum balance. So what is angular momentum balance? It says that net external torque acting on a body will be equal to rate of change of angular momentum of the body, right? So, and you also have learned that we can balance angular momentum either about a fixed point or about the center of the body. So, or about the center of mass. So we can do angular momentum balance about any point, but we will prefer to do it about center of mass of the body. So let me just write in balance angular momentum either about a fixed point or about center of mass. So how you can write it? So you can write it that summation of all the torque acting on the body, and that will be external torque acting on the bodies about either point O, any fixed point, or about center of mass. Comma means or. So that will be equal to rate of change of angular momentum. So angular momentum, let's say I'm representing by H vector, so it will be a vector quantity, and that will be either about O or about center of mass. Okay. So obviously torque also had a traction component and body force component. So let me write it down. So first it had, so this external torque had traction component. Traction means some force, distributed force or a point force acting on the surface of the body. So let's say that traction component, where I'm just writing T track, that is about, let's say, center of mass of the body, that is, and the coordinate of center of mass is x vector. Okay, so that is given by, so expression you would have learned in the class. I'm just directly writing the expression, that is sigma is equal to 1, 2, 3, and ei cross product, it is not direct product, it is cross product, sigma ei and times the volume, I mean infinitesimal volume of the body plus higher order terms of the volume. Okay, so that was traction contribution from traction, and then you have body force contribution. So let's say T body I'm just writing about point X. That was, all the terms were vanished. Only higher order terms of volume V, volume delta V was there. So this was from the body force contribution. Now the right hand side, which is d by dt of this angular momentum, that can be written as, so angular momentum of the body about any point X. So that is the position vector of that point. Okay. Let's say fixed point, or then you can take center of mass of fixed point. Let's say X is a fixed point times so position vector of the particle from this fixed point O. So this r vector is the position vector from x to the current point at which we are finding angular. I mean, we are finding angular momentum about this point x, but the point that will be taken will have position vector O, and let's say that point have mass m and velocity v. So r cross linear momentum, so that will be angular momentum. So this r vector is nothing but position vector of particle of which we are finding the angular momentum relative to the point which, about which we are finding the angular momentum. Okay. So that is, let's say, point x that is given by, so position vector will be, let's say, in this small volume of the body. Let's say we have this body here, and the point at which we are finding angular momentum, let's say this point is x. Here we have this point x. So about x we are finding angular momentum, and right now we are taking a small mass at position y. Okay, so we are, so this point has a position vector x and this point have position vector y. So we are calculating angular momentum of this point having small mass m about this position vector x, about this point which have position vector x. If we write it, it will be nothing but y minus x, that will become rho, and let's say this point has a mass m, it will be dm. I mean, let's say this point has a mass dm, and let's say this point has a velocity v, which will obviously be point velocity at point y, but this is with respect to o. Okay, or with respect to x, you can say. Okay, I mean x and o are same actually, so I'm just writing with respect to o. So this is the expression for angular momentum of this point with infinitesimal mass d. Now we have to find d by dt of this. I mean d by dt of that will be actually dx, small angular momentum of this small point mass. Now let's say we want to find the angular momentum of all the points present in the body. So we have to integrate this equation because this is the small angular momentum of this small point mass here, dm. And there will be many such points. So we can integrate to find total angular momentum. So that will be volume integral. So volume integral y minus x dm v vector velocity of with respect to velocity of point y with respect to. So now if you differentiate this, let's take that v vector. So if you differentiate this angular momentum with respect to angular momentum about point O, if you differentiate with respect to time, so you see here that we are integrating with respect to, right now we are integrating with respect to mass because we have dm here. We have not explicitly written in terms of volume. So since mass is not going to change with respect to time, so that's why the limits of this integral will not be function of time because we are integrating with respect to mass. So we can now bring this differentiation inside this integral. If this limits of this integral or bounds of this integral would have been function of time, we wouldn't have been able to bring this d by dt inside. So for more details, you can look at Leibniz rule. It tells about how to do differentiation when integral is a function of differentiating variable itself. Okay, anyway, so we will bring it inside. So that will be d by dt of the first part, dl plus t of y respect to O, plus we have to do integration. And I'm just writing it that here we are integrating with respect to mass. Here also we are integrating with respect to mass. So now that will mean I'm just applying the product rule of mass is not going to change. So that will be velocity dv by dt. Okay. And obviously this is velocity of bounded by respect to. So I just applied product tool. So these two functions were in product and they both were function of time. So I'm just a differentiation of this with respect to time plus the differentiation of this with respect to time. So finally, what will you obtain? What will you get? So, so this is, if you see here, dy by dt is nothing but differentiation, I mean velocity of point y, and dx by dt will be velocity of point x, and vy minus vx will be velocity of point y respect to x. So finally, what I can write is rate of change of angular momentum about point O will be um, I can just write here. Just wait a minute. So that will be velocity of point y with respect to O, and here there was a cross product. Sorry, I just this. Here there was a cross product. Yeah, because it will be R cross linear momentum. Okay. So you see here, this is nothing but this is velocity of point y with respect to O cross product with velocity of point y with respect to O. So two same vectors are getting in cross product. So that will be 0, because if you see the formula of cross product, so A cross B is equal to AB sine theta n cap. So sine, since angle is 0, sine 0 will be 0. So this term will go to 0 because this is nothing but the same this vector itself. So we'll be left with second term only. So that will be y minus x cross product. You can write dm, and this is nothing but acceleration of point y with respect to y. And there is it. Now, now we would like to shift from the mass integral to volume integral. So we can just write dm is equal to rho dv. So dv is nothing but in the class you would have seen that dv was, let me just write, dv was d by eta d gamma. So this is times, I'm just writing rho, dm is rho and acceleration, and dv was d gamma d xi d eta, right? And you are integrating now with respect to volume because you have taken density outside. So we are integrating now with respect to volume. So dm I have written as rho dv, nothing else. So if you solve this equation, which was done in the class, so you will obtain that this will also be a function of higher order. This will be of the order of other terms will vanish, and this will be of the order of higher order in volume. This will contain higher order terms of delta V. Actually, if you will integrate this equation, so you will get this. You will get that other terms will vanish. So for that, you'll have to integrate with respect to d gamma d xi d eta. You can refer to the class lectures for its equation. Okay. And you will obtain that rate of change of angular momentum with respect to time will be of the order of higher volume. I mean, higher order terms of volume. Okay. So if we combine all these three equations, so let's say this is equation number 1, This is equation number 3. So if you combine equation 1, 2, and 3, so finally what will you get? So you get sigma I is equal to 1, 2, 3 EI cross product sigma EI. So that was the first term times small volume delta V plus higher order terms of delta V. That will equal to higher order terms of delta V. Okay. So if you divide this whole thing with delta V, and if you take delta V to be infinitesimal, that is going to 0. So limit delta V going to 0. We divide the whole thing with delta V, so you get EI cross product sigma EI, and obviously I is going from 1 to 3 plus higher order terms of delta V divided by delta V plus, I mean, that will be equal to higher order terms of delta V divided by delta V. So since I mean, this is higher order term of delta V, right? So if we divide higher order terms of delta V with delta V, so there will be some delta V still left. And since V is approaching to 0, so these terms will approach to 0. But here in this term, there is no multiplication of delta V left, so this will not approach to 0. So only term that will be left will be this one, sigma. That will be. So this is the final equation of angular momentum balance. Right. You can ask me if you have any doubt or questions. Okay. So if you don't have any question, let me go ahead. So if we represent this in terms of in the coordinate system, E1 into E3, so how it will look like. So representation of A and B, angular momentum balancing E1, E2, E3 coordinate system. So how will it look like? So it will be, if you put I equal to 1, so that will be cross product between 1, 0, 0, E1 and cross product of sigma E1. Sigma E1 will be nothing but sigma 1, 1, 2, 1, sigma 3, 1. So that is the first term plus E2 times cross product with sigma times E2, sigma times E2 with sigma 2, 1, 2, 2, sigma E2 plus E3, so 0, 0, 1 cross product with sigma times E3, sigma times E3 will be sigma 3, 1, sigma 3, 2. Yeah, and sigma 3, 3. Okay, and that is equal to 0 vector. So if you do the cross product, finally, if you solve these equations, firstly you have to do cross product between two vectors, which you already know, and then so this will be a vector, this will be a vector, this will be a vector. So you will obtain three equations now because these are three rows. So if you equate those three equations to 0, finally you will obtain that sigma 3, 2 is equal to sigma 2, 3, sigma 3, 1 is equal to sigma 1, 3, and sigma 2, 1 is equal to sigma 1, 2. So the stress symmetry is obtained after applying angular momentum balance. Okay. So stress is not itself symmetric, it is symmetric because of balance of angular momentum. So the stress matrix is symmetric Okay, and this we have derived after considering acceleration of the body, body force, and traction on the body. So if you simply consider traction on the body, you can derive this equation very easily, because we say that let's say body is in static equilibrium, one traction is acting on this side, is acting on this side. So these two will be equal. That's why this sigma 2 1 will be equal to sigma 1 2. Um, but that is not a generalized derivation. So this derivation includes, even if this is the body and this is having some angular acceleration, or even this has some acceleration in space, then also the stress will be symmetric. So if a body has angular acceleration and now you apply sigma 2 1 and sigma 1 2, now you won't be able to derive if you do not derive this way. You cannot derive simply by just force balance. Okay, so now let's go to the problem. So let me just question one. Question one says we have to attempt this. So stress matrix. Please, stress matrix is symmetric even if body is in acceleration or there is presence of body force. Okay, so question is, this stress matrix changes from one coordinate system to another, but the stress tensor itself remains the same. So can you tell me whether this is true or false? So the question says that the representation of stress, that is stress matrix, changes from one coordinate system to another coordinate system, but the stress tensor itself remains the same. Is it true or false? Yeah, please tell me.
True, sir.
Yeah, it is true, correct. So very good. Now going to the question number two. Question number two says that suppose, and it is true because I had told you in previous class also, you can just visualize a vector. So let's say a vector is there in the space like this. So it has this magnitude and this direction. Whatever coordinate system you take, its representation is going to change in that coordinate system, but the direction of the vector is going to be same in the space. It will be aligned this side only, it will have this much magnitude only, right? Only that it depends on which coordinate system you take, its component, its projection on that coordinate system is going to change. Similarly, this is the same thing with tensor also, second order tensor also, which is stress. So stress matrix, I mean representation of stress matrix is going to change, but the tensor in the space is going to be same. So suppose a body is under stress and the stress tensor at an arbitrary point x in the body is denoted by sigma. This you already know. So further, suppose that suppose the test body is then rigidly rotated. The corresponding rotation tensor is defined by R. So you are doing a rigid rotation. So in the rigid rotation, so there will not be any deformation. Okay. There will not be any further deformation. So let us think of a coordinate system attached with the stress body, which also rotates as the body rotates. So coordinate system is also rotating and by the same amount. Okay. So the options are, first question is, what can you say about the stress matrix of the body before and after rotation? In the coordinate system attached with the body. You tell me. What can you say about the stress matrix of the body before and after the rotation in the coordinate system attached to the body? Will stress matrix change or not? Options, I'm giving you options also. Stress matrix remains the same both before and after rotation. Second option is the stress matrix transforms such that new stress matrix becomes R transpose sigma R, right? Or None of the above. So here, let me explain you the question. So there is a body which is under stress and which is given by a stress tensor sigma, and the body is rigidly rotated, and the rotation tensor is given by capital R. And now when the body is rotating, coordinate system is also rotating by the same amount. So you have to tell me, what can you say about the stress matrix of the body before and after the rotation in the coordinate system attached with the body? Okay. So yet, what will be the correct answer? Stress matrix remains the same. I mean, representation of stress, will the representation of stress remain same, or will representation change, and will it be denoted by R transpose sigma R, or none of the above? You can tell me.
Sir, I am trying. Stress
Mhm.
matrix remains the same both before and after rotation.
Why? Why is it so?
Sir, stress components are all complementary to each other. That's why.
No, they are complementary, but only the off diagonal terms will be same. I mean, you are talking about stress will be symmetric. That's fine. But when you rotate a
Yes,
matrix, I mean, when you rotate your coordinate system, right?
yes, sir.
So representation of stress in that coordinate system, will it change or not?
Not sure, sir.
Why? Actually, here the reason is so let's say this is your body, you're rotating your body, but you're also rotating the coordinate system. Okay. That's why your stress tensor will remain same because the coordinate system itself is same. No? Because let's say this was your body initially, E1 was this side, E1, E2 was perpendicular to this plane, and E2 was like vertical. And when you have rotated this body, let's say you're rotating about E2. So when you have rotated this body, your coordinate system has also got rotated and aligned along this only. Now your new coordinate system is aligned along this only, along your body only. So there's no relative change in the coordinate system before and after. So if your coordinate system would have been same and if your body would have been rotated, then now your stress tensor would have been present in this coordinate system, like which is attached to your body. But you would have to find the stress in the previous coordinate system, which was having this horizontal line. Then the representation of stress matrix would have been changed. Are you understanding something? Here we are rotating the body all
Yes,
and
sir.
we are rotating the coordinate system also. That's why there is no relative change in the coordinate system. So let's say there was a stress acting in this direction, okay, this direction. Now you have rotated your body. I mean, there was a component of stress actually. Yeah. Let's say this we are looking at this plane and the normal component of stress is in this direction. Now you have rotated the body. The normal component has gone in this direction. So if your coordinate system would have been this, then then your stress component would have been this times cos theta. And theta is the angle between the previous coordinate system and new coordinate system. So with respect to previous coordinate system, some cos theta term, or it will be cos square theta actually because you are also transforming the plane along with traction. So it will be cos square theta, not cos theta, because there are two rotation tensor multiplied. So it would have been sigma 1 cos square theta. So but now you have rotated your coordinate system also. Now your coordinate system is also like this, right? Okay. So the normal component is going to be same because the coordinate system has also been rotated. So there is no projection, your normal component of stress is still aligned along the axis of the coordinate system. Okay, so that is very good. Let me just see. Okay. Now the second question is second part B of this question. What happens to the stress tensor in body after rotation? First is the stress tensor remain unchanged. Second is the stress tensor transform to R transpose sigma R. Third is the stress tensor transform to R sigma R transpose. Yeah, please tell me. Actually, this tensor is not going to change. As I told you, that vector remains same. Tensor also remains same. Only its representation change. Anyway, it doesn't matter how much you rotate your coordinate system. It's not going to change. Anyway, but this is a special case here. The coordinate system is also rotating. And body is also rotating. The coordinate system is still aligned along the body. So it is actually relatively same. So that's why the stress matrix will also remain same. And stress tensor anyway had to be same because it's not going to change. Question 3. We have to think of a stress tensor whose matrix form has zero off diagonal components. Off diagonal components means the components which are not on the diagonal, all of them are zero. In the third column. In the third column, the components which are not on the diagonal, they are zero. Now you have to think of a new coordinate system which is obtained by rotating the original coordinate system relative to its third axis. Relative relative to its third axis. So what can you say about stress matrix in new coordinate system? We have stress tensor whose matrix form has zero of diagonal terms in the third column. We have to think of a new coordinate system which is obtained by rotating the original coordinate system relative to the third axis. And you have to say something about the stress matrix representation in new coordinate system. So the new stress matrix, you have to tell which option is correct. So the option A is the new stress matrix also has zero of diagonal entries in the third column. And B is we cannot answer the question unless we are specified the angle by which the old coordinate system is rotated. And C is the new stress matrix also has zero of diagonal entries. In the third row. Okay. And D is all the entries of new stress matrix will be non-zero. So you have to tell me what of this. So firstly, you have to do the transformation. You cannot answer this question by just looking at it. So let's take a stress tensor. So solution, I'm doing the solution. Solution for this question is like this. So let's say you have a stress tensor. So it has, so let's say this is A1, A2, and this third row will be 0. And this, let's say A11, A12, A21, A22. This is there. And this, since this will be symmetric, this will be 0, this will also be 0, and there will be A33, right? Because these two are given 0, so these two will also be 0. Now, let's say we want to find out our stress matrix in some new coordinate system, sigma m and hat. So that will be given by um, RKM sigma AP R, right? That is R transpose sigma R. Okay. So now let's say you want to find, so looking at the options, you only need to tell about the off diagonal terms in the third column. So third column has the term sigma 1 3, sigma 2 3, and sigma 3 3. So let's find out sigma 1 3, sigma hat 1 3. So sigma hat 1 3. So m will be 1 and n will also be 1. So k1 ap rp1, right? Yeah. And there will be summation over K and P. Okay. So let me do the summation. So I'm just doing firstly summation over P. So R K1 will remain as it is. So sigma K1 R11 plus R K1 sigma K2 R21 plus um, sorry, I think I'm missing out something. So here N will be 3, not 1. Because if you compare M is 1, N is 3. So this will be RP3. Okay. So this will be R13 plus RK1 sigma K2 R23 plus RK1 sigma K3 R33, right? And what will be the form of R? So this R, since you're rotating about axis 3, so let's say you have initial axis at as E1, E2, and E3. And new axis will be, let's say you have this as new axis. This will be E1 hat, E2 hat, and E3. E3 is also on this 3 hat. So E3 hat will be equal to E1 hat. So your rotation matrix, as you know, will be given by industry drive cos theta, sin theta, cos theta minus sin theta, and then sin theta times cos theta. This will be 0, 0, 1, 0, 0. Right. So you see here that your R13 is 0. This is your R13 and R23 is also 0. These two terms are going to vanish, right? And let's say this third term. So this R33 is 1. Okay. And now you have to sum up about this quantity. So this will be R11 sigma 13, right? Plus R21 sigma 23 and R31 sigma 33. So let me expand this. So this will be R11 sigma 13 R33 R21 sigma 23 R33 R31 sigma 33 R33. So in this term, you see here that sigma 13 is 0 because this term here, sigma 13 is 0, so this term will go to 0. And sigma 23 is also 0 here, so this term will go to 0. And here R31 is 0. See here, R31 is 0, so this term will also go to 0. So whole thing will vanish. So that's why you will get sigma 13 hat will be equal to 0. Similarly, you can find sigma 23 hat. So sigma 23 hat. So that will be, if you put m is equal to 2, so that will be RK2 sigma KP RP n is 3. Okay. So then you can try expanding about P and then expanding about K. So firstly, if you expand about P, so RK2 sigma K1 R13 plus RK2 sigma K2 R23. And this procedure will be similar. Plus RK2 will be there, sigma K3 will be there, and R33 will be there. Okay. So this term is going to vanish because R13 is 0. Here R23 is 0. And again, you have to expand about K. So first term will be R12 sigma 13. Sigma 13 is 0 here from, you see here sigma 13 is 0. And R22 sigma 23, sigma 23 is also 0. And here now you have R32 sigma 33. Sigma 33 is not 0, but R32 is 0, right? Because this is 0. So this will also vanish. So you have this term also as 0. Now let's find out sigma 3 3. I'm just finding out the components of third column. Okay. So now I put m is equal to 3 and n is equal to 3 in this formula. So you'll get RK3 sigma KP RP3. We'll get RK3 sigma KP RP3. Here there will be sigma. So if you now try to expand about P and then K, firstly let's expand about P. So RK3 sigma K1 R13 plus RK3 sigma K2 R23 plus RK3 sigma K3 R33. Okay. So R130, so this is going to vanish. R230, this is also going to vanish. Now let's spend the last term about K. So this will be R K is equal to 1. So R13 sigma 13 R33 plus K is equal to 2. So R23 sigma 23 R33 plus K is equal to 3. So R33 sigma 33 R33. Right. So this is going to vanish because R130 R230 and R33 is 1. So this is going to be equal to sigma 33. Okay. So you see that in the new coordinate system, sigma hat, we have proved that this is non-zero, this is non-zero, this is non-zero, this is. I mean, we do not know about this. We have not found out, but we are for sure that this is going to be 0 because sigma 13 height is 0, sigma 23 height is 0, and sigma 33 height is sigma 33 only. Okay, it is same as previous one. And since this will be symmetric, so this will also be 0. So you can just check the options. So first, this one is correct. The new stress matrix also has 0 of diagonal terms in the third column. And the new stress matrix also has 0 of diagonal terms in the third row. So this is also true because in the third row, if you see, well, this is symmetric, so of diagonal terms will be 0 because this will be the diagonal term and this will be. So this is also true. Okay. So let's go to the next question. Question 4. Say it's related to stress equilibrium equations. So the stress equilibrium equations solved can tell us what can it tell us? So option A. Option A is it can tell us about the value of stress at just one point in a body. Option B is the value of fraction at just one point. Option C is both stress and fraction at this one point. And option D is the distribution of stress at every point in the body. So what do you think? What should be the right answer? Actually, if you solve stress equilibrium equations, because stress is differentiated with respect to y, x, and z, so it will give you distribution of stress with respect to x, y, and z. Okay, you'll have to integrate those equations because those are differential equations. You'll have to solve using different techniques. Maybe if you solve using analytical method, so you'll get distribution of stress at every point in the body. So option D is correct. It will not just tell you about one point; it will tell you the whole distribution of stress in the body. So let's go to the question 5. And it will only give you stress because it is in terms of stress, because those are termed as stress equilibrium equations. So to find traction, you can find, so once you have stress at a particular point, you can find traction if you know on which plane you want to find traction and if you know the direction of that plane normal. So traction will be equal to sigma times stress, I mean stress tensor at that particular point times the plane normal, I mean plane normal vector. That will give you traction vector at that plane. Anyway, so question 5 is a prismatic bar which is clamped at the top is loaded under its own weight with body force. Body force is given by rho g 0, comma 0. That is the gravity, where rho is the density of the body. This is the mass density. And g is acceleration due to gravity. Okay. So let's say you have this body here, and let's say you have this point P. So this is L by 3. This is 2L by 3. This is a very simple problem. So this is x coordinate actually. This is positive x and this will be y. So and this is point P. So you have to, so part A is you have to tell which of the following is or are correct. Then maybe multiple correct answers related to the stress fields in this problem. So related to stress field, you have to tell which one is correct. So I think you will be able to answer. First option is sigma xx is equal to 0 and sigma yy is equal to sigma zz is equal to not 0. Second option is sigma xx is not equal to 0 and sigma yy is equal to sigma zz is equal to 0. And third option is sigma xx is not equal to 0 and sigma yy is equal to 0 and sigma zz is not equal to 0. And fourth option is none of this. So can you tell me? Which option is correct? So since the body is deforming due to its own weight, so there will be there will be force along x direction only. And if you consider this plane, so on this plane there will be traction along this direction. That's why there will be stress, sigma x6. And all other stresses will be zero because there's no traction in other directions. Okay, so uh, if you see sigma yy, so sigma yy will be zero because let's say this is direction y. So, and if you take any plane here, so plane normal will be this, plane will be this. Um, so this will be plane. On this plane, there is no force that is acting. There will be no normal force that will be acting on this plane. There's no there's no traction in this direction. So that's why sigma y will be zero. So also there will not be any shear force because uh, this is acting uniformly. It is not, it is uniform across this cross section. If there will be some distributed force, then some shear may also come in this plane. But this is not a distributed force across y. This force is the self weight is uniform. So that's why there will not be any shear. Okay, so we go to the next part. So in this case, we say that there will be only sigma x6 non-zero, other normal forces will be zero. So now part B, the longitudinal stress sigma xx at point P is given by, we have to tell about the longitudinal stress at point P, that is given by rho GL by 3 or minus rho GL by 3 or 2 rho GL by 3. Fourth option is minus 2 rho GL by 3. That's what you have to tell. So how will you tell? You have to solve stress equilibrium equations. So let me solve that. So if I write stress equilibrium equation in x direction, so that will be del sigma xx over del x plus del tau xy over del y plus del tau xz over del x, del z, sorry, plus fx is equal to 0. Okay. So you know that this tau xy will not be present because tau xy actually will not vary with y, because here you see tau xy means you have plane normals. Um this is in directions, this is direction x, and these are x, y, and z planes. So on this plane with plane normal y, so you see here, let's say you have this plane here, and it has this plane normal along y direction. Let's say this plane is passing through this point P also. So on this plane, there will be, you can say that there will be a traction along x, but that will not vary with y. So that will be same because this force is uniform across y. Okay. So del to xy by del y will be zero. In fact, in this case, del to, this tau xy itself will be zero. Because you can think of infinitesimal volume. Let me just try to do this. Okay. So you think, and this is y vector. So let's say you have force in this direction. And on the left edge also we have force in this direction. Actually, these are not shear forces. And on this face also, you have forces going downward. So there is no shearing happening in the body. Okay. So these are all normal forces actually, because shearing leads to distortion of the body, but there will be only normal displacement of the cross section. So there's no shear, so that's why this will be zero, and this will also be zero. So you have del sigma xx over del x, that will be minus of fx. And if you integrate this equation, so you can write del sigma xx will be equal to minus fx times del x. And if you integrate, so you have to integrate from at this point P, the stress will be or traction will be due to this weight below P, right? Because this weight below P will be balanced. This cross section will bear the reaction of this weight, right? So this weight will try to pull this cross section downward. So that's why we'll integrate from, so x, let's say 0 here. So we'll integrate from L by 3 to L. Okay. So we start from L by 3 and we go up to, and Fx is force acting in x direction. So that will actually vary with x. So we'll have to write as a function of x. So let's say we are at x. I mean, this is any x here, any point x, any point at a distance x. Okay. So at this point, the, let's say the small density of the body is, I mean, density of the body is rho. So, and small length of the body is dx. Let's say this much length we are taking. So this will be the small mass, and this mass will exert this much amount of normal force. So this will be the normal force acting at this cross section. So if we integrate this, the rho g and dx. Okay. So fx basically is rho g. If we integrate this from L by 3 to L minus, so we'll obtain the stresses. So integration of del sigma will be sigma xx, hence it's going from L by 3 to L, and rho g dx will be minus rho g dx will be minus rho g dx will be x, and it's going from L by 3 to L. So this will be sigma xx at L, right, minus sigma xx at L by 3, and that will be minus rho g L minus L by 3, right? So sigma xx at L will be 0 because there is no force applied here. So this will be 0. So you'll get sigma xx at a point L by 3. So that will be equal to plus of 2 rho g by 2 rho g L by 3. So option 3 will be correct. Okay. So this actually, this fx was, if you remember, this was the body force. It is force per unit volume. Okay. So that is going to be, so this was a total force that will act on this point P will be um, rho g times 2L by 3 maybe, right? Because rho you can consider as linear density, so density per unit length. Maybe. So rho g into 2L by 3, that will be the total force acting at point P. So per unit length, so divide by 12 by 3, you will get rho g. So that's why your Fx will be rho g. So that's what we have written here. You can also simply solve it without using stress equilibrium equation, because you know that at this point, the force acting is rho g into 12 by 3. That is the force divided by, I mean, that is the force that you are getting. Force per unit area actually it is. So that is itself the stress. So you straight away will get 2 rho g L by 3, right? But we wanted to do it using stress equilibrium equations. So that's why we have used this equation. That's how you have to solve using stress equilibrium equations. You just have to put the value of body force and eliminate the stresses which are 0 and then integrate. So if you do question 6, the stress distribution in a certain body is given by, so this is the stress distribution in a certain body. So this much megapascal is acting. So what you have to do is you have to find the traction vector acting on a plane which passes through the point 1 by 2, root 3 by 2, and 3, and which is tangent to the circular cylindrical surface, cylinder surface, x1 square plus x2 square is equal to 1 at that point. So the stress distribution in a certain body is given to you. You have to find the traction vector acting on a plane which passes through this point, and the plane is tangent to the circular cylinder surface given by the equation of cylinder surface is x1 square plus x2 square is equal to 1 at that point. So point is given to you because you need the x1 x2 coordinate to find out the traction vector, and you need one more thing. You need the normal vector. So you can find out the normal vector using this information that the plane is tangent to the circular cylindrical surface. So this is something known as isosurface. Isosurface means your, if you draw a line, if you draw, let's say x1 is equal to x, x2 is equal to y, x square plus y square is equal to 1, that will be a circle, right? So the combination of x and y that leads to 1. If you combine all those points, you will obtain a circle. So that is an isosurface, because on that surface, combination of x and y is leading to a constant value. That means iso means same. That is leading to the same value. So that is isosurface, and gradient to the isosurface is normal to the surface. You can see its proof on the internet that it's very easy. Just have to apply Taylor's expansion and you get the proof. So gradient of isosurface is normal to the isosurface. So let's represent this isosurface as f is equal to x1 square plus x2 square, and that is equal to 1. If I try to find gradient of that, so that will be nothing but del f by del x1 even del f by del x2 e2. So that will be 2x1 even plus x2 e2. So this gradient will be normal to the isosurface, and we need a normal vector because we want to find out the traction on a plane which is tangent to the cylindrical surface. So tangent, so this gradient will be plane normal to the tangent plane, right? So if you want to find out n, so n will be nothing but a unit vector. So you just find gradient of f and divided by its magnitude. If you do that, so you'll get 2x1 e1 plus 2x2 e2 divided by 4x square x1 square plus 4x2 square, right? So finally, you get x1. Okay, and this here you can put the value. So you can take 4 common, so that will be 2. So 2 and 2 will get cancelled, and x1 square plus x2 square is equal to 1. Finally, you will get x1 e1 plus x2 e2, right? That will be your normal unit vector. So now if you put the x1, x2 coordinate, so coordinate is 1 by 2, root 3 by 2, and 3. There is no x3, so there is no need of the third coordinate. So you put x1 is equal to 1 by root 2, 1 by 2, and x2 is equal to root 3 by 2. That is 1 by 2 e1 plus root 3 by 2 e2, right? And now you have sigma also. So sigma, you can just put value of x1 and x2. So you have this expression here. You put the value of x1, that is 1 by 2. This will be 50. This will be 50. This will be minus 50 root 3, and this will be minus 50 root 3. So 0, 50 minus 50 root 3 minus 50 root 3, 0, 0 minus 50 root 3, 0, 0. Okay. And you know that traction vector on a plane with normal n. So that is given by nothing but sigma times n. So you have sigma also and also just multiply both of them. So if you multiply 0, 50 minus 50 root 3 minus 50 root 3, 0, 0. Oh, sorry. This will be 50 because it has to be symmetric. Right? And if you multiply with traction vector, the 1 by 2, root 3 by 2, and 0. So finally, what will you get? You will get 25 root 3. Just have to do matrix and vector multiplication. So finally, you will get this. Okay. So your traction vector finally will be given by 25 root 3 e1 plus 25 e2 plus, minus 25 root 3 e3. Right? This is your final answer. Going to the next question. So you have to say that in the absence of body force, the equilibrium stress distribution for a certain body is, so stress distribution is given as sigma 1 is A times x2, sigma 2 is, so A, B, and C are constants, and x1 and x2 are coordinate system. Sigma 1 is sigma 1, which is equal to x1, and sigma 3 is equal to sigma 1 plus sigma 2 by 2. Okay. So all other sigma ij are 0. Also, the boundary plane. So there is a certain body, and that body has a boundary in terms of plane, and the equation of that boundary or plane is given by x1 minus x2 is equal to 0. And this boundary is free of stress. So also the boundary plane for the body is free of stress. Okay, so there will not be any traction here. Okay, on this boundary. So you have to find the value of A, B, and C. Firstly, you have to find the value of C. And then find the value of A and B. Okay. So you have been given with stress tensor and there's no body force. It is given to you in the absence of body force. So you can use this information and put this into stress equilibrium equation. Let's see what happens. So you have one stress equilibrium equation. Another condition given to is that on this plane, the body force is and the body is free of stress, means traction vector will be zero. So firstly, this is also isosurface. We will find the gradient of this surface, which will be normal vector, unit, and we'll find unit normal vector. And we will multiply the stress by unit normal vector, we'll get traction and we'll make traction equal to zero. That will be second condition. Using these two conditions, let's see whether we are able to find out A, B, and C. So first condition is, so solution. So let's solve stress equilibrium equation. So you know that sigma ij comma j plus bi equal to 0. So that is the stress equilibrium equation. So that can also be written as del of sigma ij comma del xj plus bi equals 0. So if you now is writing first in the first direction, so that is del sigma 1 by del x1 and del sigma 1 2 by del x2 plus del sigma 1 3 by del x3 plus b1 equal to 0 and body force is 0, so b1 is 0. So I'm just not writing b1, so this is obviously 0. So because body force, there's no body force in the body. So del sigma 1 1 over del x1, so that will be 0. And because sigma 1 1 is not a function of x1. And del sigma 1 2 over x2. So 1 2 over x2 will also be 0 because that is a function of x1. Del sigma 1 3 is 0 because all the other stresses are 0. So actually all three components in this equation are 0. So we are not going to get anything. So this is 0 anyway. So let's go to the second direction. Sigma 2 1 over x1. Sigma 2 2 over x2. 2 3 over x3 is equal to 0 because there is no body force. Okay. So sigma 2 1. So sigma 2 1 over x1 is 1 because 2 1 is x1 of itself. So sigma 2 1 over x1 is 1. Sigma 2 2 over x2. So sigma 2 2 over x2, that will be c. So we can just write c. Here we have got something. Sigma 2 3 over x3. Sigma 2 3 is 0 because all other stresses other than this will be 0. So this 0 will equal to 0. So c you have got as minus 1. And you will not get anything from third equilibrium equation. You can try. So let's go to the next part. So we have to find the value of A and B also. So we have the value of C, and to find the value of A and B, we'll have to find the traction vector and put the condition that on that plane, the traction is 0 and stress is 0, traction is 0. Okay, so let's find out the unit normal. So let's find the gradient of that f. So f is x1 minus x2 equal to 0. So gradient of f is del f by del x1 e1 plus del f by del x2 e2. So del f by del x1 is 1, so that is e1 vector, and del f by del x2 is minus 1, so that is minus e2 vector. And if I find out normal, so let's say, yeah. So if I try to find out normal, so this divided by its magnitude, so this will be e1 minus e2 divided by root 2, right? So this gives you the normal vector. And now you have to find traction. So traction at this plane with n cap is given by sigma times n, and that should be equal to null vector, right? So now let's solve this. So sigma is obviously first is sigma 1 1, which is ax1, then sigma 1 2 ax, that is x1, and sigma 1 3 is 0, and sigma 2 1 is also x1, and sigma 2 2. So sigma 2 2 is bx1 plus cx2, and c is minus 1. So that will be bx1 minus x2. So that's what I'm writing here. And this sigma 1 3 0. This will also be 0, and then sigma 3 3 sigma 1 1 sigma 2 2 by 2. right? So this is given to you. And then you are multiplying this with this vector. So 1 by root 2 will come here actually because it is a scalar. And then its first component with E1 is 1, E2 is -1, and E3 is 0, right? So that's what we have done here. And if you multiply this and equate this equal to 0, 0, 0, so this 1 by root 2 will go to the right hand side, it will become 0. So this AX1 minus X1, that will be equal to 0, first equation, because you are just multiplying this row with this column, and that will be our first equation. Then you multiply second row with this column. So you'll get x1 minus bx1 plus x2, that will be equal to 0, and third is 0 is equal to 0. So from first equation you get a is equal to 1, and from second equation what you get, I think I have done most. Actually this is not x2, this is x1 only. Just wait. This is ax2 x1, okay, bx1 cx2, okay. Okay, yeah, okay. So from this, actually, we can just deduce that x1 is equal to x2 on this surface, right? On this plane. And we are putting traction equal to 0 on this plane only, so that this condition will hold. So that's why this x2 you can substitute as equal to x1. If you do that, so x1 minus x2 will be 0 here. So you will only left with minus bx1 equal to 0. So b will be 0. Right. Sorry, not be 0. X1 is equal to x2, so that will be 2x1 minus bx1 equal to 0. So b will be equal to 2. That's fine. So here, just in this equation, you put x1 is equal to x2 because on this plane, x1 is equal to x2. Okay, so now you have the value of all three. So C is 1, minus 1, A is 1, and B is 2. That's how we can find. Let's go to the next question. Question number 8. It's a question number, yeah. So the question is, in the absence of body forces, do the following stress components satisfy the equation of equilibrium? The stress components are sigma 1 is equal to A x2 square plus nu times x1 square minus x2 square. Sigma 2 is A x1 square plus nu times x2 square minus x1 square. And sigma 3 is A nu x1 square plus x2 square. And sigma 1 3 is equal to sigma 3 1 equal to 0, and sigma 2 3 is equal to sigma 3 2 is equal to 0. And sigma 1 2 is equal to sigma 2 1 is equal to minus 2A nu x1 x2. Okay, so you have to prove that in absence of body forces whether this satisfy equilibrium equation. So let's see. The first equilibrium equation is L sigma 1 over del x1 plus L sigma 2 1 over, yeah, L sigma 1 2 over del x2, L sigma 1 3 over del x3, and there's no body force, so that will be equal to 0. So let's put that. So del sigma 1 1 over del x1 will be 2 nu x1 plus del sigma 1 2 over del x2 will be minus 2a nu x1, right? Yeah. And here also there will be, and obviously this both will cancel out and this that will lead to 0. So 0 will be equal to 0. Right. You can just differentiate sigma 1 with respect to x1. So that will be 2 nu x1 and sigma 1 to x2 will be minus of 2 nu x1. And then going to the next equilibrium equation. So first equilibrium equation is satisfied. So going to the next equilibrium equation. So sigma 1 over x1 plus del sigma 2 over x2 plus del sigma 3 over x3. So del sigma 1 over x1. So that will give you minus 2a nu x2, right? And del sigma 2 over x2. So 2 over x2 will be 2a nu x2 and sigma 3 is 0. So the second equilibrium equation is also satisfied. Okay. And then third, del sigma 1 over del x1, del sigma 2 over del x2, sigma 3 over del x3. That is equal to 0. So del sigma 1, so 1 is itself 0. So first term is 0. So sigma 2, that is also 0. And sigma 3. So sigma 3 over del x3. So sigma 3 is not a function of x3. So that differentiation again will be 0. So yes, these are satisfying the equilibrium equations. Okay. So now we have 2 more minutes left. So maybe I can give you some question to do your homework. So question is question 9. So suppose we have a general stress matrix in E1, E2, E3 coordinate system. A new coordinate system is obtained by rotating the original coordinate system by 180 degree. But this rotation is about E axis, about E2 axis, about E2 axis. The stress matrix in the new coordinate system is evaluated. Which of the following is true? Tell. Okay. So you have to firstly derive rotation matrix. Someone is saying something. You have to firstly derive rotation matrix. So that is given by so firstly, instead of writing this, you can just do derive the new stress tensor. Stress matrix in new coordinate system. So you know that, you already know that sigma hat, that will be equal to R transpose sigma R, right? And this is in E1, E2, E3 coordinate system. Right? All these three are also sigma also are also. So to get the components of stress matrix in new coordinate system, right? You have to do this. So you know that any matrix Rij, I mean this can be any matrix. So let's take any matrix A. So you know that any matrix Aij will have A times Ei, A times Ej dot Ei. You can write like this, right? You would have studied in the previous classes. So this Rij can also be written as R times Ej dot with Ei. This is different. And Rej is nothing but Ej hat, because we have rotated Ej by a smaller amount. That will give you Ej hat. So this Rij is Ej hat dot Ei, right? So now let's try to find out the rotation tensor R. We are rotating about E2 axis. So let's say we have this E1 here, E2 here, and E3 here, and we are rotating. So let's say we rotate it by this amount, so that this is new E3 hat, E1 hat, this is theta, and this E2 hat is equal to E1, E2, E2. So this R11. So R11 is I will be 1, J will be 1. So it's angle between dot product of EI and EI, E1 and E1 caps, that will be cos theta. And then you have R12. So that will be dot product between E1 and E2 hat. So E1 and E2 hat will be 90 degrees, so that will be 0. And then R13, that will be dot product between E1 and E3 hat. So E1 and E3 hat, so that is their angle between E1 and E3 hat is 90 minus theta. So that will be cos of 90 minus theta. So that will be sin theta. Similarly, you derive other components. So that will be 0, 1, 0 and minus sin theta, 0 and cos theta. Now your rotation is minus 180 degrees. So you put, sorry, your rotation is 180 degrees. So you put 180 degree at the place of theta, you'll get R, and you put R in this here. So you'll get sigma hat. You already know sigma. So sigma can be sigma 1, 1, 1, 2, 1, 3, 1, 4, 1, 5. I mean, sorry. So 1, 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 3, 3, 1, 3, 2, 3, 3. So finally you will get sigma hat. So sigma hat. So let's take sigma to be x1, x2, x3, x4, x5, x6, and x7, x8, x9. So if you find sigma hat, your sigma hat will turn out to be, you just do this R transpose R sigma. That will be, so that will be x1, x5, x9 will remain same, but others will change. So that will become minus x2, that will become x3, and that will become minus x4, and this will become minus x6. You can try. Please try it out at your home. This will be the answer. Just multiply, you just put theta is equal to 180 degree here. And do R transpose, you do transpose of this matrix, then sigma matrix, and this R matrix. So first multiply these two matrices, and whatever will be the resultant matrix, you multiply that matrix with this R transpose matrix. Finally, you should get this. So I'll stop here for today. You can, if you have any doubt, you can type in the discussions group. Okay, thank you.
Thank you, sir.